All right, everyone, we are back and we are going to go through our problem set 5 solution videos. So let's go ahead and get started. Looking at these stress strain curves here, what is the stiffest material? That's going to be basically the black curve. So steepest slope. Toughest, that's a little bit of a tough one. I would say maybe green. Yeah, I would say green is probably the safest bet for sure. So I'd say green because, again, the area under that curve here. And then let me undo all that. Here we go. So I would say green. For the strongest ultimate tensile strength, that'd be right here. So that would be our black curve again. Highest yield strength, again, once we are no longer linear, which I would say maybe somewhere like here approximately. Highest, so that would also be black. Most ductile, that would be red because it's the largest here. So that would be my red. Most brittle, that would also be the black curve. And let's see, for the black curve, indicated the quantitative values. Excellent. So this would be my yield strength. So it'd probably be about close to 70 MPa. The ultimate tensile strength would be here. So I'd say that's about, let's say that's about 85 MPa, approximately. This would be my yield strain, and that would be, let's see if that's 2, probably about 1%. Or basically 0.01. My strain at failure would be here, which is probably about 4, well, that's 6. Yeah, probably about 4.5% or 0.045. And I think that's all that's required here. Failure strain, failure stress. Oh, failure stress, actually, yeah. So the stress at failure would be probably about right here. So about close to 50 megapascals. Yield strain, blah, 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 all that other good stuff. Fantastic. All right. Now let's get to some fun problems. I have the following ceramic material in the stress state seen here. So again, first step, we have our coordinate system, so check. Material, ceramic, so we know Young's modulus is equal to 300 GPa. Our nu is equal to 0.2. Poisson ratio. So remember, nu is our Poisson ratio. We're given some of these things. So now let's look at our stress and our strain tensors. So we have an arrow that's pushing down in the 3-3, so there's going to be a stress in the 3-3, and we should expect that to be negative. There's also here, top of the cube here. So this top and then this face are open. Material is attached to the cube, basically here and here. So they're physically attached on those planes. So we see a stress in the 1-1 as well, and that should be positive. If it's attached, there could be no strain in the 2-2, meaning that there's a stress in the 2-2, and we're not really sure about what that's going to be. It kind of depends on the values that we're seeing here, because we're pushing down, so that means it would want to expand out, but we're also pulling here, so it's not clear. There's thermal expansion coefficient, which we have. No friction between the walls, the dimension here. So we're given the thermal expansion coefficient, but we're also given the final dimension of the 3-3. So we know what the strain in the 3-3 is, and we know that that's going to be a negative value, but we have that. We also know there's going to be a strain in the 1-1 too. So basically, we actually know what this one is too, because we can calculate that little area here. So we're left with unknowns of this, and of this, which is great. 3 unknowns, we can solve for this. A little bit of a red herring with the thermal expansion coefficient, but yeah. Ooh, actually, no. There's a little bit of this is a nice continuous problem that we're going to work through. So let's go ahead and get to it. So let's go ahead and unknown force. Let's solve for all these stress strain tensors. So now let's put it in here. I am going to use this pre-notebook. So now I have my Young's modulus is this. Oops. My nu is going to be 0.2. My strain in the 2, 2 is 0. My strain in the 3, 3 will be the final dimension, which is going to be 30 centimeters, 30 times 10 to the minus 2, minus my initial, which is 35 times 10 to the minus 2, divided by my initial, which is 35 times 10 to the minus 2, and that will be negative, as we can see here. All right, what else do we know? We also know that sig11 is going to be equal to basically 90 times 10 to the 3 positive, because we're in tension, divided by 35 times 10 to the minus 2 squared. Minus 2. Oops. Minus 2. Let's make sure. Minus 2 squared. We're going to snooze on that restart action. And I'm just going to put this. I'm always a little bit crazy about that. Excellent. So we have that. We have the strain in the 3, 3. So those are the values we know. And we also know the strain in the 2, 2, 0. So, okay, I think we're in good shape now to proceed. So we'll shift enter that. Let's look here and to see, make sure that we're all good in terms of, we're writing everything in terms of our unknowns, which are going to be the strain in the 1, 1, which we don't know, which is shown right there, and then also the stress in the 2, 2 and the stress in the 3, 3. All right. So now we can solve those three equations. And strain in the 1, 1 is positive, makes sense. The stress in the strain in the 3, 3 is negative, which really makes sense, which is good. And then the stress in the 2, 2 is positive, or is a negative, excuse me. So as we kind of push down and it expands out here, it kind of shows you, and again, you can look at the magnitude. That stress in the 3, 3 is actually, if we compare that to the sig11, let's look at that numerically. Much smaller stress here than here. So obviously that's what's leading to that compressive stress. So it wants to pop out, and so it all matches. Fantastic. So we're actually asked for the force in the diagram. So we know now, actually I'm going to define it right here. I'm going to pull out basically all these values so that we can show that this equals this. We'll show that sig22 is this, and then we will show that sig33 is equal to this. Good. So now what we have is, for the sig33, so solve where sig33 equals a force divided by an area, which is 35 times 10 to the minus 2, and that would be that force. It's quite large, but makes sense because I don't really practice these problems ahead of time. Excellent. So we've got our values. So full stress strain tensor, we already have all those values. Write out the principal stress values. We are in principal stress, so those would be those values right here. What about maximum shear stress? Well, we know the rotation of maximum shear, which would be a 45 degree. But in terms of the maximum shear stress values, you could write these in terms of basically sigma 1, sigma 2, sigma 3. And then you could find the maximum shear stress of basically like your 3 more circles. But because we're not in plane stress, we're not going to be able to answer that question effectively for this particular stress state in terms of what we've covered in this class. So leave that for another problem in another class. So same thing here. Rotate 17 degrees clockwise from this. We can't do that. So this is not a possible, problem. Turns out that the room temperature actually changes from room temperature to 98. The final dimension after the puck explodes, and the temperature change is still this. So now it's resolving this problem. So can we do it? Well, so all we have to do to change in here, we'd have to define it, what our alpha is. So I'm going to go up here. I'm going to type in what our alpha is. Our alpha is going to be now, the delta T is going to be, what was that? 98. So the delta T is going to be the final temperature which is 98 minus 25. Our alpha is going to be equal to this. Alpha equals 0.7 times 10 to the minus 6. And we are going to quit our kernel locally, quit the kernel, and then now we're going to basically solve everything once again. So that's, oops, nope, too much. So let's go ahead, we'll plug this in. Everything else remains the same. It's just now we're adding that thermal expansion coefficient to it. It'll take some time once you reset the kernel, but again, you have to do that each time to clear those variables. So make sure that that is indeed the case. So it's thinking. And remember, if we're not in plane stress, excuse me, we can't do the rotations. You'll have to learn that in another course. So let's solve here. And you see the values shift a little bit, but not too significantly. So I'm just going to go ahead and kind of cheat here and have this as sec33 and solve for our value. And then these would be the other values that we have. So excellent. Thermal expansion here, because again, we're dealing with such large stresses, it's not going to make a huge, impact per se. So we wrote this, we wrote out the values. Again, we're still in principal stress. The rotation would be 0 degrees. In principle, no pun intended, the rotation of maximum shear would be 45 degrees, but we are not in principal stress state, and we can't answer this question either. So wasn't I kind? I gave you a problem where you didn't have to do all these rotations. So let's see if I'm continuing to be as kind in the next problem. So I'm working with a new pipe, and actually before we get even into the pipe, I am going to clear this kernel. So I'm going to quit my kernel here. I'm going to also scroll down to something that may be useful. Working with a pipe, I have a length, I have a thickness, I have a diameter, I have 2 strain gauges, and we have 2 measurements for the strain. Pressurized, we don't know what the material is. This is our pressure vessel. We have our coordinate system. So we need to first, whenever we hear diameter and thickness, we don't know what the material is, so we're going to leave this. This is just an unknown here. We don't know our nu, but we do know that our diameter is going to be 45 divided by 2 times 0.0254, because I want to convert the inches to meters. The thickness is going to be, I believe that's a 0.2 inch thickness, yes. So 0.2 times 0.0254. That's a good number to kind of just have on hand. Or excuse me, not a number, but a conversion factor per se, to make sure that you can move between those two. So always be aware and that we're clear on those things. I don't know why I didn't do this. Maybe it doesn't like these that are undefined. So our radius over our thickness. So it is indeed, remember, if R over T is greater than or equal to 10, we can move to our thin wall pressure vessel, which means we have our coordinate system. We don't know what our material is, but now we can say that in the one direction, that's going to be longitudinal. This will be hoop. Every other stress, we're in plane stress state here. So we have the strain longitudinal, strain in the hoop. In this scenario, our strain in the 2 direction, in the 2 strain gauge here. So this strain in the 2 strain gauge is equal to the strain in the longitudinal. This strain in the 1 strain gauge is equal to the strain in the hoop. So now we can use these equations to solve for everything else that we want here. So we are told, we're told the delta P2. So del P in this problem is equal to 4.9 times 10 to the 6. So now that we also know that E, actually we can even say, let's shift enter this. Let's shift enter all of these equations. And then we're going to solve 2 equations. I'm going to call E1 is equal to, again, our EH is set equal to 0.004658. And E2 is equal, our second equation is going to be equal to EL is equal to 0.00105. We should also know that those two values make sense because, again, the hoop strain is always going to be larger than the longitudinal strain, the same with the stress. So we're going to solve E1, E2. And we have our values. What does this look like? So this is about, let's see, 10 to the 9. So this is 100 gigapascals. Nu is 0.3. That's a metal. So we're working with a metal. Once we have those values as well, let's go ahead and define that here. Let's say that our nu is equal to this. So our nu is this. Our Young's modulus is this. So now we can say sig h, sig l, EH, EL, even though we know those already. So we have all those values. We're already in principal stress. Maximum shear stress, we could actually, that the rotation is going to be 45 degrees. We could actually find that because remember, in our Mohr circle approach, hoop is always larger than longitudinal. We're in this stress state here. So if I'm looking at, oops, let me undo that. Control Z that. There we go. We're already in the principal stress state here. Oops, why does it keeps wanting to? So I'm just going to go over here, and this distance here will just be hoop minus longitudinal over 2 is the radius. So that would be equal to my tau max for any thin-walled pressure vessel system in plane stress state. Find the stress state for a 48-degree counterclockwise rotation from the principal stress state. So this is nice because we can utilize, so my sig OG, my original stress state, is also equal to the principal stress state, so sig OG, and that's going to be equal to, again, normal, sig H, sig L, doesn't matter here, and then the shear stress value. So if I need to rotate that, I need to bring in these fellas, or these definitions here. This is my rotation matrix. So if I need to rotate to a new coordinate system, I'm just going to take my old coordinate system, sig OG, or actually I'm going to do t dot sig OG, and then slash dot, my theta goes to, so just temporarily setting theta to value. Theta goes to what? So I'm doing a 48 degrees counterclockwise. Counterclockwise is always going to be a positive rotation. Shift enter. Those are my values. Nice as that. That's why we love linear algebra in this class. Fantastic. All right, so now we have a red ceramic material. So coordinate system, we're already told Young's modulus is equal to 300 GPa because it's ceramic. Nu is equal to 0.2. Between two immovable and rigid lubricated surfaces. So again, it's squished, but it's not attached, at least for right now. Forces are symmetric and 15 kilonewtons, so we can look at the stresses that are going to happen here and the strains now because we've done step 1, step 2. What are the final dimensions? Right at the full stress strain tensor. Okay, so now let's get into, we got one. We have one more? We do have one more. Oh, yeah, I like it. Okay, so what's happening here? So we do have a stress in the 1-1. It's going to be positive. We have a stress in the 2-2, which will also be positive. When we pull, again, it's sandwich, it's rigid, but it's not, it's not necessarily attached. So there's not going to be stress because when we pull here, the material is going to shrink down. So there's going to be no stress. There will be a strain in the 3-3. And there's also going to be a strain in the 1-1, or strain in the 2-2, excuse me. And there's going to be a strain in the 1-1. So we know this, this is 0. So we need to solve for 1, 2, 3 right here. Fantastic. So let's go ahead and let's get that set up, and we will quit our kernel. And then we're going to go back up to the top of our little notebook here. So quit my kernel. We know this is still the same. We know that the sig 3-3 is equal to 0 in this particular problem. I'm also going to make some definitions of, because we read in the problem, dimension in the 2 is 78. So I'm going to say L2 naught is equal to 78 times 10 to the minus 2. These are all the initial dimensions. L1 naught is equal to 35 times 10 to the minus 2. And then L naught 3 is, or L3 naught is equal to 4.8 times 10 to the minus 2. Fantastic. We're not dealing with any temperature here, so we'll keep the alpha here, but I wonder if I messed up that previous problem. If I did, it's just a order of magnitude error. But we'll set this as 0. So now we can proceed, except for the fact that we need to define that this is actually going to be a little bit, we need to look into this here. So we have a force, and in this system, so our force is equal to 15 times 10 to the 3 kilonewtons. So it's positive because we're in tension, but I need to find this cross-section, this area here that this is acting on. So this is going to be L2 times L3. This here is going to be L1 times L3. So I need to divide those areas. So for example, my sig 1,1 is going to be equal to F divided by L2 naught times L3 naught. And then, oops. So remember, it's always cross-sectional area. Sig 2 will be equal to F divided by L1 naught times L3 naught. And so now we can shift enter all of those things. We can also look at our values here and make sure again that we don't have anything that we didn't want to deal with. Okay, so, and actually we already have those values, but we can solve for it just the same. And those will be our strains. Now we need to actually figure out the final dimensions. So when we look at these now, so I'm going to actually pull these out and let's define them here. So strain the 1,1 is equal to this. Strain the 2,2 is equal to that. Strain the 3,3 is equal to this. And then now I'm going to solve E11 is equal to, set equal to L1 final minus L1 naught divided by L1 naught. So that's going to be your value here, here, and then also here. I'm just going to train this to 2,2. So strain 1,1. It's extremely small, these strains. So it may look, this will be L2F, L2 naught, L2 naught. And so you can see this because it's a little bit larger. It's not showing you for the really times 10 to the minus 7. We probably actually won't see a value necessarily here. Oops. It's trying to bring up a help page. And then finally we can do here 3, and then we'll do this. Oops. 3, oops. And then L3 naught, and then L3 naught. And you can see here, so see it's not giving us that because of just the super small value. But you get the picture. Okay, so now we're told that suddenly there's a shear strain here. And then it's saying, okay, well, if there's a shear strain here, so now we have an epsilon 1,2, epsilon 1,2. If we have a shear strain, we also have a shear stress. So E12 is equal to 0.123419. So I'm going to solve when E12, set this equal to 1 divided by y, Young's modulus, times 1 plus nu times sig 1,2, because now there is going to be a stress to 1,2 here, and that is my sig 1,2. So I now have a stress to 1,2 here, I have a stress to 1,2 here. So now I actually have to, if I want to find the principal stress state, I'm not in the principal stress state, so I need to do sig OG sig OG is equal to sig 1, normal stress, and then shear stress, sig 1, 2, because I'm in plane stress in the 1, 2 plane. So now I need to, again, go back down here. I'm going to pull out my rotation matrix, go all the way here. If we want to find both the direction and the principal stress state, I need to do T dot sig OG. When I do that, and if I look at it in matrix form, basically gives me 3 equations. The third equation is the equation for my new, shear stress in the rotated coordinate system, or the new stress state. So I'm going to pull out this third equation, and I'm going to ask the question, if I'm in the principal stress state, it means that when I rotate, this new shear stress needs to be equal to 0. So what is that rotation in terms of theta? Let's find out. So I'm just going to say it's this. Again, I can choose either one. They're all, symmetric. So I can say T dot sig OG slash dot theta goes to this. And you see this value is effectively 0. So this is my principal stress state values here. I can similarly do the same thing here. If I want to, instead of not make this 0, but maximize to find my maximum shear stress, I'm going to take the derivative of this function with respect to theta and find what value sets it equal to 0 to maximize it. So that would be my rotation to maximum shear stress state. And then all I'd have to do is do T dot sig OG. Theta goes to this. And you see, this would be the value. And we can confirm this because remember, you see how this is at like the center of our Mohr circle? If I take this value, our principal stress state, this, minus this, so if I take it this, minus this, and if I divide this, so I'm going to, again, minus is a plus, divide it by 2, I get the same exact value. So that's beautiful because it all makes sense now. Principal stress state, maximum shear. What is the stress state at 19 degrees counterclockwise from the principal stress state? This is a cool problem because this is my principal stress state here. So if I'm going to do another rotation, 19 degrees counterclockwise from that principal stress state, what I would do is take this value and I would do plus 19 degrees. So that rotation to get to principal shear plus that 19 degrees, and then it would give me this value here as well. So it's pretty close to, actually, let me get rid of this. Actually, that's much better. I had a little Mathematica issue there, but that'd be it. So linear algebra approach is really, really nice. Let's look at the previous example, but now there's no forces and the temperature decreased from room temperature to, actually the temperature decreased from room temperature to 100 C. I think it's, it needs to be increased. So that's just an error here. Increased typo. So now the temperature is increasing. So there's no forces or no stresses initially. So what's happening here? Temperature increases. These rigid walls are going to constrain it in the 3-3. So there's going to be a stress in the 3-3. There's not going to be any strain in the 3-3. There will be strain in the 1-1 or the 2-2. I don't know why I keep thinking that's 1-1. There will be strain in the 1-1 because, and then there's going to be no stress here, no stress here. So let's go ahead and solve for this. I'm going to quit my kernel. So I'm going to say now we have this. It is 10 minus 7 though. My change in delta T, my final temperature is 100, or actually decreased from room temperature, yeah, increased. So 100 is my final, 25, and then, so now that it's doing this, so let's look at the previous example. All right, so let's go ahead. I've got this here, I've got this here. So we also know that the sig 3-3 is not 0. I'm going to delete everything here except for this. So I'm going to say that E33 is equal to 0. I'm going to say that sig 1-1 equals 0 and sig 2-2 equals 0. Get this. We'll look at these values, make sure that we have everything that we need, and then we'll solve in the last step. So we need to solve for sig33, epsilon 1, epsilon 2, epsilon 1, epsilon 2 should be positive, sig33 should be negative. Let's see. If that's the case. Positive, positive, negative, fantastic. We got it. Now it's saying that the so now also that the 0, 0, 1 and 0, 0, 1 is attached. So if that is the case, there's going to be a stress in the 1, 1, and then this will be 0. So we can do that. I'm going to just clear again, clear everything. And then I'm just going to say, now we also have, instead of sig11 being 0, it's E11 equals 0. And then we can just run this. So we should expect that the stress, again, stress in the 1, 1, stress in the 3, 3 should be negative. Strain in the 1, 1, strain in the 2, 2 should be positive. Let's see if that's the case. And if it is, we've successfully completed definitely the most difficult problem set in this course. Negative, negative, fantastic. And they're symmetric, perfect. So that's our solution video. So we'll see you next time. Thanks. Bye.